First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
All right, so when the board comes on, I have a picture of a vector. It looks like what you guys call an array in geometry. So like a line with an arrow on one end. But actually a vector is 2 points. And so the starting point is called the initial point, and where the arrow is, that's called the terminal point. It's not like a ray, because a ray, the arrow keeps on going, and for a vector, it stops at that terminal point. Vectors for us are numbers. So they're a new type of number for you. Previous to vectors, the numbers you've been using, 1, 2, 3 over 4, -7, pi, e, those numbers are technically called scalars, scalar quantities. And a scalar just represents a number, we call it a magnitude. A vector represents a magnitude and a direction. That's why the vector has an arrow, to signify its direction. The most elementary comparison of a vector to a scalar is speed to velocity. Speed is a scalar quantity. If you're driving 50 miles per hour, you're just driving 50 miles per hour. Your velocity tells you the speed and the direction. So the velocity is what we would call a vector quantity, because it gives not just the magnitude, not just the speed, but also the direction. Okay, so I put a couple of vectors on this graph here. I actually was doing this at the end of class yesterday, and so I have a vector u and a vector v. I'm going to mess with vector v right now. So I'm going to signify the initial point and terminal point for vector v as a and b respectively. So I'll call the initial point A, I'll call the terminal point B. And so vector V, and that's a notation you may see for a vector, the little arrow above it, is equal to vector AB. Now, when I write a vector with 2 points, where 1 point is the initial and 1 is the terminal, the initial point must go first and the terminal point must go second. So the vector AB is different from the vector BA. Principally, they go in opposite directions. So if the vector was BA, the arrow will be pointing at this end. And in typeset print, so in books and stuff, a vector with one letter is normally just put in bold. They normally don't put the arrow above it. And even me, just writing, when you guys have an understanding that I'm talking about vectors, which you're going to do now, I'm going to stop putting the arrow above a one-letter vector. If it's 2 letters, I'll put it. But if it's just 1 letter like U or V, I'm going to stop doing that. All right, so I would like to take a note of the coordinates of points A and B. Well, let's say I start with point B. What are the coordinates of point B here? 5, 3, correct? And what are the coordinates of point A? 2, 2. Now, what I'm going to do is I'm going to put this vector in a form that's very beneficial for a lot of math we do. That's called component form. I'm going to put this vector V, in component form. So its location on the graph is going to change when I put it in component form. And basically, to put a vector in component form, we put the initial point at the origin. A vector in component form has the initial point at the origin of point 0, 0. So let me take this vector and let me put them in component form. He doesn't want to move, but he's going to move. All right, I put the vector in component form right before your eyes. I didn't hide it. It wasn't a secret. He's now in component form. His initial point is at the origin. When a vector is in component form, we write the components of the vector in angle brackets, and the component of the vectors are the coordinates of the terminal point. I don't need to write the coordinates of the initial point because it's going to be 0, 0. So when it's in component form, these are called angled brackets. We write the components in angle brackets, which is 3, 1. So that vector in component form is the vector 3, 1. The vector 3, 1 is exactly the same as the vector AB. They have the same magnitude, they have the same direction. No matter where I move this vector on this graph, vector V is vector V. It can go wherever. It's just very beneficial to have its initial point at the origin. So one of the first things we're going to ask you to do, given a vector at 2 different points, we're going to ask you to put it in component form. Unfortunately, you're not going to be able to just drag like I dragged vector V. You're going to have to do some math. So I would like you to look at the coordinates for points A and B and look at what we got for our components of vector V and subtract, correct? So if you look at it, 5 minus 2 is 3, and 3 minus 2 is 1. And when you subtract, order is important. So if you notice, what I did is B minus A, or more precisely, the terminal point minus the initial point. So component form is terminal minus initial.
When you say component form, it's always at the origin. This is where like it starts from the origin.
Right, yes. So once it's in component
So
form,
initial point is at 0, 0.
after when it's in component form, yes.
Yeah.
So component form is terminal minus initial. That order is important. Anytime you subtract, order is important because A minus B is not the same as B minus A. Unless, of course, A equals B, then they're both 0. And I'll do an example of putting the vector in component form. That's fairly easy. I mean, all of this stuff is easy, especially for people like me and you, but I'll look at an example nonetheless. There he is. We're not quite ready for that guy yet. Let's erase this junk. Let's take a look at number 1. So you can see it says find a component form of the vector AB, and with initial point A and terminal point B. Now again, to put a vector in component form, you do terminal minus initial. So I'm going to do B minus A. But don't assume you're always going to do B minus A, because if this was a vector BA, then the roles would be switched, and I would do A minus B. And we are later in this assignment going to ask you to put the vector BA in component form. So just make sure you're doing terminal minus initial. What's terminal and what's initial could change. But in this case, terminal is B and initial is A. So terminal B is 8, 1, and A is -5, 3.
In this instance, the second letter is always going to be terminal, right?
Correct, yeah. So when written with 2 letters, when this type of notation, the first letter is always initial, the second letter is always terminal. It has to be written in that order. So the order of the letters must go initial, terminal. All right, so let's see what we get. 5 minus -5 is 13. And 1 minus 3 is -2. Now it's in component form. We put the guy in angle brackets. All right, so that's how we put a vector in component form. And the reason we put vectors in component form because it makes a lot of the math we do with vectors easier. All right, so got that out the way. Next, I told you a vector consists of 2 things, magnitude and direction. We talk about direction tomorrow. Today, we're going to talk about magnitude. So magnitude of a vector. So the notation for the magnitude of a vector, say the magnitude of vector V, the notation is the same notation you use for the absolute value of a scalar number. So it's that same notation. And you're going to use this notation a little bit later for something called the determinant of a matrix, and also something called the modulus of a complex number. So this notation is used a lot, but all of those things really, absolute value, magnitude of a vector, modulus of a complex number, they're all very related as you learn more math. Now, what does a magnitude of a vector mean from a graphical standpoint? It just represents the length of the vector. That's all it is. It's a fancy word for the length of the vector. And for those of you that do a lot of independent math studies, or you watch a lot of different math videos on YouTube for enjoyment, you will also see this notation, which is exactly the same thing. So the double bar and the single bar, they mean exactly the same thing. You may hear people refer to this as the norm of a vector, and that word means the same thing as magnitude and length. So these are things you may see. The deal is when you get to more advanced math classes, they start using this notation and this word, but it means the exact same thing. All right, so let's go to the vector we were looking at thus far. I think it was that red guy, vector V. And let's see if we can figure out how to find his magnitude. So I'm looking at this vector V right here. And he's in component form, and that's where I want him when I'm finding magnitude. So the magnitude is how long this red line is. That's the magnitude. How can we determine how long that red line is? Pythagorean Theorem, correct? So if you look, you can form a triangle where the magnitude of the vector, the length of the vector, is the hypotenuse. And in this triangle, you have two sides. This side is 3, which happens to be the first component of the vector. And this side is 1, which happens to be the second component of the vector. And if you just understand Pythagorean theorem, then you would understand that the magnitude of V is going to be the square root of 3 squared plus 1 squared, which is the square root of 10, which is just a little bit more than the square root of 9, which is 3. So it's around 3.1, and maybe 3.04 something, but it's around 3. Let me say it like that. So because people can answer the question, how can I find the length of V 2 ways? To me, the most efficient way is to say Pythagorean theorem, but people can also say distance formula. One of those x1 and y1, or x2 and y2, whichever one you want to label it, is 0, 0. So you end up just squaring those components. So in general, for magnitude of a vector, so if the components of vector V, say I call them V1, V2, then the magnitude of vector V is the square root of V1 squared plus V2 squared. And now, of course, this formula is only if the vector is in component form. And if the vector wasn't in component form, what I do, I just put it in component form, and then I'm able to do this formula. So I'm going to go back to the assignment. I'm going to look at a couple examples of finding magnitude. One example, the vector will be in component form. The other example, it will not be in component form. So we got this guy. Now that's the one not in component form. Okay, so number 5. So notice the vector's in component form. How can I tell? Angle brackets plus, it's not 2 different numbers. There's only one pair of numbers, so it must be in component form. And they want me to find the magnitude. So I know that the magnitude of vector V is the square root of the sum of the square of the components. So this is the square root of 5 squared plus negative 11 squared. Now this isn't that bad of a number because this is 25 plus 121, which is 146. And the square root of 146 is going to be a little more than the square root of 144. So it's going to be like 12.1. But in many cases, you would have to find this answer in the calculator. Here, it was just an easy number. And the problem is, people don't know how to type this guy into the calculator if they have to use the calculator. And the main issue that people do every year is they want to write negative 11 squared like that. The calculator reads this as, okay, you want me to square 11 and make it negative. It's going to read that as negative 121, meaning it's going to do 25 plus negative 121, which is negative 96. It's going to take the square root of negative 96, which isn't a real number, and it's going to say error, non-real answer. So you have to make sure when using a calculator that when I write a negative number squared, I write that guy like that. Now, let me demonstrate. So here's a calculator. So here you can see I've already done the problem. Notice I have the negative 11 in parentheses. Life is good. Everything is great. But what if I was one of those people, and I see those people every year. They're great people. Like, don't get me wrong. They're nice people. But I didn't put this guy in parentheses. Again, that's error, non-real answer. Whenever it tells you error, non-real answer, that typically means you're taking the even root of a negative number. And so again, you have to put, you have two choices. Either put the negative 11 in parentheses, or when doing this process, just make both numbers positive. Those are the two options. Put the negative guy in parentheses, or just make both numbers positive. All right. So that's magnitude of a vector when in component form. What about when not in component form? So here, oh, that's just component form. There's nothing great about that problem. So here they want me to find the magnitude of the vector, AB, and it's not in component form. So I'm going to put it in component form. Now, do I have to? No. I can do the distance formula if I want. The square root of x2 minus x1 squared plus y2 minus y1 squared. I can do that. But I prefer just to put the guy in component form and do what I do. So I'm going to put them in component form. B is terminal. It's negative 1, comma, negative 9, minus 6, comma, negative 8. So this is negative 7, comma, negative 1. So say for the sake of notation, I call that vector V. So therefore the magnitude of vector V is the square root of negative 7 squared plus negative 1 squared. Again, these happen to be easy numbers. They just randomly came out easy like this. This is 49 plus 1, that's 50. So that's a little more than 49. So that's going to be 7.1. So if he's not in component form, I recommend putting them in component form. Or you can just do the distance formula. All right. I have two things that I'm going to basically do them together. And that is adding vectors and scaling vectors. All right, so I'm going to go back to my geometric interpretation of a vector. Let's go back up here. And if you notice, I have two vectors here. I've only been messing with one. Obviously, I wanted to make use of the other. So I'm going to bring vector u into this party. So, and vector u is stubborn. This guy, oh, he's moving now. He hasn't been wanting to move all day. So there's vector u. And I put them in component form because, you know, this math we do, we like the vectors being component form. And I think you can clearly see the components of vector u are 2, 3. And of course, we've already stated the components of vector v are 3, 1. Now, I want to add these guys. And so this is something, again, I don't know where you've gone in physics and stuff, but in physics, you add forces. You'll learn later vectors represent forces. So how do we add those forces? We put one force, we put the initial point of one force on the terminal point of the other force. So we want to do that. Let's put that back to center. So I'm going to put the initial point of vector u on the terminal point of vector v. The resulting vector, I'm sure you guys have heard of a resultant force. The resulting vector is u plus v. So there's no, let me show you what the resulting vector looks like. So let's draw a new vector. Let's go lime green on these guys. So this is the resulting vector here, and that vector represents u plus v. Now, if you look at the components of the resulting vector, again, this lime green guy, maybe that wasn't the best color now that I'm looking. I should have chose better, maybe next time. But the resulting vector has the components 5, 4. Now again, this was just a geometrical interpretation of adding vectors, how they look for adding forces. But you're going to do it more analytically. You're just going to have vector u and vector v, and we're going to ask you to add them. Can you see what you do to these numbers in order to get this result?
Yeah.
Just add them, correct? So if you notice 2 plus 3 is 5 and 3 plus 1 is 4. So this is how the addition of vectors or the addition of forces looks on the graph, but in the abstract, we're just adding the components. First plus first and second plus second. All right, one last thing, I'm going to scale these vectors. Well, not these, I'm going to scale one of these guys. I don't need you anymore, young fellow. And I may need you some tomorrow, vector u. I'm going to keep you around. But you've been stubborn, you don't like to move. There you go. We're going to probably use you tomorrow. All right, so vector v, I'm going to scale this guy. And what that means is I'm going to multiply vector v by a scalar, a regular number you've been knowing all your life. And so I'm going to scale it to where you can see the result. So I'm going to find 2v. What do you think I would do to the components of v in order to get 2v? Multiply by 2, right? So that would be 6, 2. But how does that look? How does that vector relate to this vector? So let me plot the vector 6, 2. And let's see what this guy's red. Let's go orange. So this is the vector 6, 2. Here's 6, and here's 2. So as you can see, it's the exact same vector. It's just twice as long. It's going in the exact same direction. So when I scale a vector, it's going to go in the same direction, but it's going to be scaled. So it's going to be either bigger or smaller, depending on the value of the scalar. Of course, if this was 1/2 v, it would be in the same direction, but half as big. All right, so I got 2 more examples. So one example, we're just going to scale the vector. And you're going to say that's too easy, and I'm going to agree with you. The other point, we're going to scale and add or subtract the vectors. And you're still going to say that's fairly easy, and I'm still going to agree with you. All right, so this example right here, vector v is 9, -4. They want us to find 5v. What's the answer? 8, correct? So 5v just means we multiply these components by 5, 45, -20. Okay, sorry, apologize for the simplicity of that guy. My last example, people do make mistakes on. And I'm going to show you what exactly they do. So here I got 6v minus 5u. So I obviously got to multiply b by 6 and u by 5. That's obvious. And then I can subtract them. So, okay, 6b, so here's b, so that's 36 comma negative 42. No one disputes that. Okay, 5u, so multiply 5 by u, that's negative 20 comma 5. Subtract. 36 minus negative 20 is 56. 42 minus 5 is negative 47. That's pretty easy. That's the way I do it. But some of you are going to do it differently, and you have a right to do so. If you notice on this problem, I multiply by positive 5, and I'm okay with that. Some of you are going to multiply by negative 5. Okay, that's cool. Like, I don't have a problem with it. So let me look at that aspect. But let me show you where you make your mistake when you do this. So you're going to multiply by negative 5, and you're going to get positive 20 and negative 5. I don't have a problem with that. The thing you need to understand is when you multiply by negative 5, you have used this negative sign. It's no longer a subtraction problem. It's an addition problem. So if I add, you can see clearly I get the same two numbers. The mistake students make is they multiply by negative 5 and they still try to subtract. In that case, you can see I get the wrong answer. I'll get 16 and negative 37. So you can either multiply by 5 or negative 5. The choice is yours. However, if you choose to multiply by negative 5, then you've used the minus sign. This guy is now an addition problem. Yeah, as long as you turn it into an addition problem, you add is going to be the right answer for if you multiply by negative 5. And if you multiply by positive 5, of course, you haven't used the negative sign, and so you have to subtract. So the method is yours. Just be careful to do the method properly. All right, I'm done. If no questions, you can start the little assignment.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.